Okay, I am recording. Back to that screen share. So, so there was a video that I posted of me going through these notes, and I'm hoping everybody has a chance to do that. And then let's see. Let me just take a moment here to close up a bunch of these windows. Since I've already got, when you host these meetings, you get like a million. You get a million windows popping up. So, all right. And so now I'm going to click on the assignments link, Jedi 1.0, and we'll go to Jedi 1.0. So, am I sharing this screen or not? Yes. So, so last time I asked you to get busy on implementing all of the classes that we talked about. So, so with Jedi 0.0, you probably already have the expression trait identifier class. And then here you're implementing a class called fun call. These are all examples here of fun calls. So a fun call has an operator, just an identifier, and then it has a list of 0 or more operands, which are the inputs to the function. And I think, so here's the grammar for that. And I think that somewhere, yeah, stuff like 3 plus 4, basically we're going to parse that into add 3, 4. And I think, see, yeah, and so all of these, the execute method for executing a fun call will just be to go to the ALU and call execute. Next, we introduced special forms. And special form is just an empty trait that extends the expression trait. And the only reason I have it there is to have like a kind of a catch-all term for types of expressions that have weird execute algorithms. Okay? And toward that end, I introduced conditional, that's if-else, conjunction, that's and, disjunction, which is or. And the reason that these have weird execute algorithms is they have what are called lazy execute algorithms. So they don't execute all of their inputs. They only execute the bare minimum they need in order to get the answer. That's in contrast with fun call, which executes all of its inputs and then passes that list of arguments on to the ALU. That's sometimes called eager execution. So we have eager and lazy. There are different forms of lazy execution, conjunction and disjunction. Both use what are called short circuit execution. Conditional uses conditional execution. Okay, and so from this diagram, you should be able to put together the class, and then when you read through the notes, hopefully you can put together the execute methods. Another special form is declaration. So these are examples of declarations up here. Anything that begins with the word def, and then there's an identifier, the name of the thing you're defining, then an equal sign, and then here, for example, you're going to have any kind of an expression at all. So a fun call, a special form, a literal, another identifier, etc. Okay, the execute for declaration, remember execute gets this environment as an input. So all it does, like for example, let's see, here, it would execute pi times e. It's an expression, so I'm going to execute it. That's going to give me a value, 8.47 or something. And then I put into the environment the identifier pi bound to 8.47. And now later on, when I say, hey, what's pi? Right, well, this is an identifier, so we execute the identifier, it looks it up in the environment, and says, oh, so the identifier pi is associated with the value 8.47. And then also you'll see here the return value is just the notification, okay. I gave you a bunch of code, so I'm expecting that you've installed all of this code as best you can in Jedi. Okay, so today, were there any problems or questions with that I can answer? You can just type something in, I think, pop up, or you can speak up if you have a question. Wow, okay, you guys are smart. So today, we're going to talk about Parsing Jedi 1.0. And if you scroll down here, I've given you these Jedi 1 parsers. Okay, so we're going to talk a little bit. So what you need to do right now, if you haven't already, is in the context package, create a class called Jedi 1 parsers and copy paste this into that file. So why don't you take a minute to do that now? Okay. So let's go through this. For most of you, this will probably be the most complicated part of this. So I've got some includes up here, some notes, and then like the thing starts here. If you hear noise, I don't know if you can hear that noise in the background, but my granddaughter is out in the front yard just yelling her head off about something. So let's walk through this, ask questions if they come up. So Jedi 1 parsers extends regex parsers. Regex parsers comes from this import here. Okay, and it means something like, I don't know exactly what it is, but I think it means that you can use regular expressions. You can include regular expressions in your parser. So and we'll see exactly how we're going to use that shortly. So the principal parser, the starting point, this is the parser that gets called from the console, is called expression. Okay, it's a def because I'm defining a function. And this here means that this is a parser that takes a string as an input and returns an expression as an output. And by expression here, we're talking about the expression hierarchy that that you've been assiduously defining, hopefully. Okay. And then here we have, so one way to read this is that an expression is a declaration, so it's a def, or a conditional, or a disjunction, or it's a failure. Okay, so failure here is a special primitive that Scala also comes from the combinator library. And basically, if we get there, that's going to throw an exception that we're going to catch back in the console and say, hey, we didn't understand what you just typed in. Now, I'll just say this quickly here, but I'll go over it again later. You might say, hey, well, there's a lot missing from this list. For example, what about conjunctions, or what about fun calls, or what about identifiers or literals and so forth? Those are all going to fall out of disjunction. So the definition of disjunction is going to be one or more expressions separated by the or operator, that double pipe. And so if it's just one, well, that one could be like just a fun call by itself, or it could be an identifier by itself, right? So disjunction here is being used very broadly, like a disjunction possibly consisting of just a single expression with no or operators in it. So fun call in that sense is a disjunction. All of the other forms of expressions are all going to be parsed by disjunction. Another thing that I'll mention is, remember, this is Scala, functional programming, combinators, etc. Declaration, conditional, and disjunction are all parser functions. Remember, a parser is a function, maps strings into expressions. Okay, so these are functions that are going to be defined below. You can take a peek and see down here, right? I'm defining these guys. Okay, and so remember that this pipe symbol here in the context of parsers is a combinator. What's a combinator? A combinator is a function that takes several smaller functions as inputs and combines them into a more complicated function. There's no rule in Scala that says that a combinator function has to be a prefix function. It can be an infix function. It can be like an infix symbol like we have here, right? So even though this just looks like a little pipe between these two, you're actually calling a function that takes two inputs, declaration and conditional. And this whole thing is now a more complicated parser, and I'm combining that with another one of these pipes into an even more complicated one. I guess failure is just a function that returns that string invalid expression. Okay, so these are combinators, and that's really like I just think one of the coolest applications of combinators that I've seen in a long time. Okay, let's focus in on declaration here. And I'm going to, I don't know if this is going to work. I'm trying to see if I could get this to work. Just a few minutes ago, I'm still getting parser errors here. So see if that works. Declaration does not like the declaration yet. Here is my project, my Jedi project, and I'll give you like a little tour of what I've done. Here's my special form class. Look, that's it. Special form extends expression. That's all there is to it. And here's declaration. Okay, I shouldn't even be showing you this, but because it extends special form, so I just, I just followed the diagram. It has two pieces in it. It has the name. Let me just see what I called it in the diagram here. Yeah, I didn't quite. Oh, it's just called expression there. Okay, so I lost my window. Here it is. Rename this expression just so it'd be consistent with the diagram. Okay, and here's how I'm going to execute it. Right, here's my execute function. I'm going to execute the expression part. Right, here's an example. That's an example of a declaration. Okay? X here would be the name, and add 2, 3 would be the expression. So here I'm going to execute the expression, which by recursion, that should return 5. And then in my environment, I'm going to associate with the name, that's X, the value that this produces. And then I'm going to return the notification. I think it's okay that it returns. You know, my notification class, I've got done, okay, and unspecified. Okay. So that's my declaration class. It's a case class, and I'm not quite sure why Jedi 1 parsers is not liking it. It seems to like it now. Declaration. Oh, because it's saying that it should be returning an expression. All right, I'll just have to fix that in a moment. So let's take a look at this code then. So declaration is a parser, which is going to return a declaration. It's mad here because I said it would return an expression. It's returning a declaration. But that's okay, right? Because declaration is a special form, is an expression. So declaration is a subtype of expression. And so, so we are returning an expression, just something more specific. Okay, and then here is the rule for declaration. The declaration begins with the string def, followed by identifier. Now, identifier is another parser that's defined below, followed by the string equals, followed by, and here's a recursive call back up to expression again. Okay, again, from the combinator perspective, followed by is a combinator. It's taking these smaller parsers and combining them together. You can think of a string as being the simplest parser. It checks to make sure that the string is actually literally equal to the string DEF. Otherwise, you know, it rejects it. Okay, so this is checking that the string begins with that the string that's coming into declaration begins with DEF, and then it's followed by an identifier, and then there should be an equal sign, and then there should be another expression. Okay, and then here's transformed by, and now we go inside here. So if the first string below was def, then we should see def here in the tree that this is produced. Next will come the output of the identifier parser. We'll just call it ID, as just a name I'm giving to it. Right? ID is a name I'm giving to it. It should be an instance of the identifier class. Okay? Followed by, should be an equal sign there. And then EXP is the name I'll give to the output produced by the expression parser. Then what I'm going to do is I'm going to call the declaration constructor, and I'll feed it ID and EXP. Again, if we go back and just take a look at that parser, right? His constructor wants an identifier and he wants an expression. And it's a case class, so they've automatically generated a companion object with an apply method in it. Oh, I see. Now it seems to be happier. Okay. Now, if it's not, let's see, I'm going to go back to, we'll go back to here again, where were we? Jedi 1 parsers. Okay, so let's say that the string did not begin with DEF. So the declaration parser fails. Okay, so whatever the string is, a string is what, remember, At the console, we print prompt, okay, and the user is typed in like a bunch of stuff. Maybe it's garbage. And that comes in as a string. And the first thing we do in the console is we use this expression to try to parse that string, and it tries to parse the string using declaration. Okay, and if it succeeds, then a declaration is produced, and the declaration gets executed. Okay, maybe. Maybe let's just take a quick look, just in case some of you might have forgotten that. So this is in context, console. Here's our REPL, read, execute, print loop. We're reading in CMMD, that's our command. And here we're doing printing out the result of executing the command. Here's execute, CMMD is a string. This line here is how we call the parser. So parsers, that's up here. Parsers is our Jedi 1 parsers. Parsers.parse all, I'm not sure what that means, but then it wants to know which parser to use. Well, we want you to use expression parser. What string should I parse? Well, we want you to parse command. Okay, and that's going to, in our case, this expression here would be a declaration if it was something like def x equals 2 plus 3, right? And here's where we execute it. That'll update the global environment, and that'll return OK. And here we're taking OK and converting it to a string, and it's going to get printed. Okay? Now, if that string that the user typed in doesn't match this rule, remember, you can also think of grammar rules as patterns. And so if it doesn't fit this pattern, then what this pipe symbol means is, okay, well, try to parse it with this one then, the conditional parser. We come down here to the conditional parser. Okay, this guy is going to return a conditional. Remember, a conditional. Let me just do this, just so I keep having to switch back and forth between these two screens. Here's conditional down here. It's also a special form, right? Which this is the if else, right? And so maybe it's a conditional. So we'll try to parse it with the conditional parser. Here's the conditional parser. It takes a string as an input and returns a conditional as an output. And here is the pattern. It should begin with the string if, followed by a left paren, followed by an expression, followed by a right paren, followed by another expression. So this would be the then clause. So what we're talking about here is, there's an example, hopefully. Yeah, so this is an example. So if, and then in parentheses, some condition, and then this would be, sometimes this is called the consequent or the then clause, and Pascal used to have to write then in front of this. This would be through's lesson 4, then 3 plus where else x. And then here is the alternative or the else clause. Okay, so there are 3 expressions involved here: the condition, the consequent, and the alternative of the terms that we're using. And here we see the conditional has a condition, a consequent, and an alternative. And all of these are just expressions, is all we really know. Okay. Now, here's the other thing that's sort of interesting is that the alternative, the else part is optional, right? I mean, think about that. Uh, you're always doing stuff like, this is sometimes called a one-way condition. You'll say, well, if X is less than 0, then throw an exception, a positive number expected. There's no else, right? Because you throw an exception, that's going to like terminate the thing right there. So that's typical in programming, is to just have a consequent a then clause, but no else clause. And so the way we express that in Scala is with this OPT, which means optional. It's equivalent to the question mark that is used in the less formal terminology. So what OPT says optionally, there might be this string else down here followed by another expression. And here is this whole thing from this parentheses to that parentheses. That whole thing is the optional part. Maybe it's there, maybe it's not, right? So there are two possibilities. So we're going to, when a string comes in and it's parsed, remember all of this is one big parser and it's going to generate a tree. There are, and also appreciate expression, expression, expression. These are all recursive calls back up to the top to this expression parser. So there are two possibilities. Either the else clause was there or not. Now, OPT, what I've told you, and I hope it's stuck in your head, the way that OPT combinator works is that it returns an optional value, either a sum or a none. So one possibility is the output tree looks like this: if followed by left paren, followed by COND. That's the name that's what I'm going to call the output of this expression parser, condition, followed by a closing paren, followed by cons here. That's the output of this expression, the consequence, followed by none. That's the output of OPT if there was no else. Okay, now I have two variations. I have a conditional class, and it has two variations of the constructor. One that takes two inputs, the third, the default value being null, I think. And then the other possibility is exactly like this, except instead of none, it returns sum. And inside sum, here's the output of this parser, the string else followed by alt. That's going to be the output of this expression. And so now I'm going to make a conditional here. Okay, so I promised I would return a conditional, and I am. Right, so I'm being asked if I can repeat what OPT does again. Okay, so let's see if I got that. So if you go through this example that I gave, that I pointed you at the beginning of class, right? It gives like a little explanation there about REP and OPT. Here's like a version of this that's using OPT. And it explains, like none or some here. But let's see if I can come up with a quick explanation again. Jacob, you're getting errors in the lines after the declaration. Yeah, well, that's because there's a lot that hasn't been defined yet. So I've had to comment out most of my parser. You're going to get errors until you're almost done with the parser. Let's see. What could I say here? Right. So remember in an EBNF grammar, you can have something be optional. So for example, you might have something like this number oh, let's do it this way. Okay, so let's just take a look at that. Let's see if I can. Make the font a little bit bigger, hugely bigger. There. Okay, so this might be like a kind of a little grammar rule here. A number has got this is one or more digits followed by, here we have a decimal point and one, again, like a sequence of digits, right? So this would be the integer part followed by the decimal part. But the decimal part, this question mark here says, well, the decimal part is optional, right? So the way that we would express that in Scala is so first of all, this would be rep. I'm taking some liberties here. This is kind of what this rule would look like in Scala. I'm gonna have to change that. I have to change that to star. Rep means one or more. Zero or more, this means one or more. But let's just change this just so it's accurate, matches the Scala better. So this means zero or more, but in Scala, Scala used to have this this star here. I could literally, this would be the same rule, but they've changed it to a prefix operator, rep. Okay, and here we see rep again for this part. Okay, but this question mark here, which applies to the entire decimal place, this turns into OPT. Okay, and what it means is what this means is either a decimal point followed by a bunch of digits or the empty string, nothing at all. Okay, and because a number may or may not have a decimal part. Okay, and so what happens here is that the output of OPT so the output of this parser here is the output of this parser, which could be a decimal point followed by a bunch of digits, but it's inside of a sum object, or the output of this parser might just be none. No, there was no decimal part. By contrast, the rep output would be something like this. Suddenly I'm looking at my keyboard and I can't find my. Let's see. No, I'm not right about that. Sorry, close your eyes for a second. For example, if the sequence of digits that you typed in was 1, 2, 3, 4, then the output of rep is a list of the digits consisting of whatever the output. This parser, outputs a single digit. And so, but we're repeating it. So this is going to be a list, or it could be, since it's 0 or more digits, here, it could be that. Could be the empty list. Well, you said 0 or more. That means 0 more. So there were 0. Or here's a list for like each repeat of the parser. All right. So where was I? Maybe back here. Hopefully that is helpful. Let's see who else has got a question here. Oh, good. Good. I understand now. So, okay. Right, so we're using that OPT here, okay? And so our parser has to check for the transformer. The way I call this is literally the parser up to here. That's the parser, and that's going to produce a tree for us. And then this means transform by, and everything here, I call this the transformer. Okay, so it takes that tree and has to transform it into a conditional expression, which it does so here and it does so here. Okay. Now, let's say, so this string that the user typed in didn't match this pattern. Well, so then what this pipe means is, okay, we'll pipe it into disjunction. Take the whole string, pass it into disjunction. Maybe something will happen there. And here's the disjunction parser. Gosh, I can't believe how much of this I gave to you. So now disjunction, I might produce a disjunction. Let's take a look at the disjunction for a minute. Here it is. Disjunction extends special form, okay, and it has a list. I have 2 or more operands here. Disjunction is or, right? A or B or C or D, that kind of stuff. I have an example of it up here. Yeah, here is an example of a disjunction. It's a bunch of expressions with this double pipe, the or operator between them. Okay. I can't guarantee that I'm going to produce a disjunction here because a disjunction can degenerate into some simpler form of expression. So the only thing I know for sure here is that it'll be some kind of an expression. Here's my rule for, let's see, do I have the grammar here for disjunction? Not quite. Now, here's the rule I'm operating with. Let's. Right, so for me, a disjunction. I'm sorry, I'm going to share this with somewhere else. I'll type it in here. So for me, a disjunction is one or more conjunctions followed by, so this would be so here it is informally. A disjunction is a conjunction followed by, and then here in parentheses, an or sign followed by another conjunction, and you're to repeat that 0 or more times. Here's the same thing in Scala. Conjunction followed by, and instead of star, I have to say rep, but what's inside is exactly the same. Okay, so conjunction, and the way I would say this in English is a disjunction is one or more conjunctions separated by the or operator. Okay, so that's exactly what this rule says. Now, for this rule, there are two possibilities. Remember, this is rep. Take a moment and think, what is the output of rep? The output of rep is a list. Okay, there are two possibilities. The first case here is nil. Remember I said a disjunction is one or more conjunctions. Well, what if it's just one conjunction? Well, then these additional conjunctions didn't happen. That's the empty list. Con is the name I'm giving to the output produced by this conjunction parser. Okay, so if it was a conjunction followed by nil, I'm just going to return the conjunction. If it was a conjunction followed by some more conjunctions, so more would be the name I'm giving to the list that this produces, then I'm going to construct a disjunction. Now, my disjunction constructor, what he wants is a list of expressions as input. So I'll take this expression. Remember this guy? This is the cons operator. I'm going to cons it on to, I'm sorry, what did they call it? The constructor. Maybe, I think they did call it cons. Maybe cons is the old Lisp term for it. But takes this guy and adds it to the front of this list. So this whole thing is a big old list of expressions, and I'm going to turn it into a disjunction. Disjunction is one of my classes. One little twist here is that normally the output of this would not be a list of conjunctions. It would be a list of conjunctions mixed in with these stupid or operators here, right? So more here is going to be not a list of expressions, but just a list of any, just a list of there are going to be some expressions in there, but it's going to be mixed in with the or operators. And so before you could actually make a disjunction, you'd have to fish through this list and, remove, extract out all of the actual expressions. It'd be a lot of work to do that. So Scala has this neat feature, which is that little arrowhead there. Okay, remember what that means. Whatever is behind the arrowhead, in this case, the or operator, verify that it's there, but don't include it in the output. So the output here is going to be a pure list. This more here now will be a pure list of expressions, which is exactly what disjunction is expecting. Okay. Hopefully everybody's getting the hang of it. So now I've got to define the conjunction parser. And uh-oh, I forgot to put it in. Okay, and that's because that's where you come in. You're going to be kind of on your own at this point. But I do give you the EBNF rule in traditional notation for this. What is a conjunction? A conjunction is, in English, one or more equalities separated by the AND operator. So the definition of conjunction, you could just copy paste this pretty much. Okay, call it conjunction and replace conjunction with equality. Replace this with the double equal or the AND operator, right? This is equality as well, and here instead of make a disjunction, you're making a conjunction. So this happens. So this happens here where we called the conjunction parser. We came down here and we looked for one or more equalities separated by AND operators. What is an equality? Here's the equality parser. An equality is one or more inequalities separated by equal signs. So I'm allowing, for better or worse, I'm going to allow this kind of a thing. So that is a legitimate Jedi expression, and its value is true if all A, B, C, and D are all equal to each other. Okay, so you can have multiple things that you're testing in a single expression, so they all have to be equal to each other. It's my interpretation. Here's my definition of inequality. An inequality, now here I'm not so liberal. An inequality is a sum followed optionally, there's option, OPT, followed by another sum, and between the two sums would be one of the inequality operators, less than, greater than, or not equal to. Okay, so this kind of a thing no, I'm not allowing that. And I mean, there might be some way to make sense out of what the user meant by this thing, but as designers of programming languages, it's partly our job to try to enforce some good programming habits. This would be terrible in a program. Imagine you're like the poor guy who has to maintain this code and figure out. You'd have to C programmers love this. They love to write really cryptic looking code here. It takes you 2 days to sort through exactly what was meant by that. So an inequality is two sums separated by one of these three operators. Okay, I didn't do less than or equal or greater than or equal. You can do that if you want. But since that second part is optional, it could just be a sum by itself. Okay, we come down here to sum, and I'm going to temporarily skip over this because it's complicated. The sum is one or more products separated by plus or minus signs. And I've actually given you the code for this. A product, where's my product parser? A product is one or more terms separated by a multiplier divide sign. A term is a fun call or a literal or an expression inside of parentheses. There's a literal, it's a bool or a real or an integer or chars, and then lastly, an identifier. Now, here, how to get this to, so I wouldn't have too many errors. I defined, let's look at my definition of identifier. You're supposed to work this out yourself. So, so don't look too carefully at this. Here is the pattern for an identifier. So this pattern here, an identifier is so simple that you can describe it using a regular expression. So remember, we have two ways of describing patterns. A pattern, simple patterns can be described using regular expressions. More complex patterns are described using grammars, EBNF grammars. So my definition of an identifier is any alphanumeric string that begins with a letter. Let's review a little bit. What is an identifier? So identifier is a name. So a name that you might choose to define, right? So X, Y, Z, or temperature, or percentage, or Dow Jones average, or Fahrenheit temperature, something like that. Okay, so whatever, you can choose any names, your programmers can choose any names they want to define things, provided that the names they choose fit this pattern. Alphanumeric string beginning with a letter. And so here, let's just study this regular expression. So this regular expression is any letter, lowercase or uppercase. This regular expression here, oops, what did I just do? This regular expression is any letter or digit. Okay, and then that last letter or digit, you can iterate it 0 or more times. So what I've done is I just copy pasted this regular expression into a raw string. Remember, this is the raw string. And then this .r means convert that into a regular expression. We have two ways of expressing regular expressions. You can express them as strings, or Scala has a regular expression class. Okay, so I've taken this string and .r turned it into an instance of the regular expression class. So what the parser does is it asks if a string matches this pattern. If it does, so here, that's the string that matched the pattern. I call it name. And then I'm going to use that to make an identifier. Remember, the identifier wants a string as an input. And this produces an identifier as an output. You have to do the same for integer, real, and bool. They'll look very similar to this. Chars is really tricky. Chars, remember, a chars looks like this, right? It's something like right? That's a chars. It has quotes in it, right? So my regular expression, and this is really complicated, has to have a quote in it. So I'm escaping the quote here. And then this thing means any character at all, except for quote. Any character except for quote, repeated one or more times, and then followed by another quote. So that's pretty complicated. If you don't understand it, you don't have to understand it because I gave it to you. And I'm assuming that characters is the string that matched this pattern, right? And so then I'm going to take these characters, I get rid of the quotation marks, and I feed it to my chars constructor. So I've given you that one. Okay. How are we doing? Questions? Okay. Oops. How did that happen? I guess I have to go here to the parsers. Right. So that's tracing through the parsers. Now, you'll notice that the way that I've done things might seem a little bit weird. For example, I said disjunction is our conjunctions. So I have to go back over here. A disjunction is made up of conjunctions. And now, why not a conjunction is made up of disjunctions? Why did I do it this way? Well, the order of parsing, reverse order of parsing is the order of precedence. So defining a disjunction to be made up of conjunctions means that if you have a mixed expression, for example, let's see, share this again with you. If you had, for example, something like this, suppose you have an expression like this. Okay, well, there's two interpretations of it. It could mean, or it could mean and that makes a difference too. It's easy to think of examples where it makes a difference. Which one of these is the right, which one of these is the right interpretation? Okay, so our rule, we're following the convention most programming languages follow, which is that and has higher precedence than or. So this is the correct interpretation. Now, to enforce precedence like this, what you have to do is that or gets parsed after and gets parsed, which is why in my parsers, right, disjunction has conjunction inside of it. It's the same thing with plus and minus, with products and sums. So a sum is made up out of products, right? So it's a sum of products rather than the product of sums. And that guarantees that if you have a mixed expression, 2 plus 3 times 5, right, that's going to be 17 rather than 25. That's the multiply is done first. The multiplications will be lower in the parse tree than the sums. And typically when you execute like a parse tree, you execute from the bottom up. That's the recursive algorithm, right? So that's why they get executed first. So that's how precedence is done. Right? So here I'm explaining all of this. So 2 plus 3 times 4, multiply gets done before plus. So, and here 5 minus 12 divided by 3, well, division should be done before subtraction. So that's why sum is product separated by plus or divides. Here is the kind of tree, for example, if I gave it the sum parser, so think of sum as the parser, if I gave it this string, 2 plus 3 times 4 is input, here's the expression, here's the fun call it's going to generate. You're adding 2 with the result of multiplying 3 and 4. Now, there's another issue in parsing, which is associativity. Here, for example, I have 2 times 3 times 4. Well, is that 2 times 3 and then multiply by 4? Or do I do 3 times 4 first and then multiply by 2? Which way is it? So here are the two different interpretations. Is it that, or is it that? And the happy news is it doesn't matter, because they both produce the same answer. In mathematics, what we would say is that multiplication is associative. So this is actually a rule of arithmetic here. A times the quantity B times C is equal to the quantity A times B times C. So not an issue. Associativity axiom is also true for addition. This is another axiom of arithmetic. Unfortunately, division and subtraction aren't associative. So here I am doing 60 divided by 12 divided by 4, right? And that's different from, that's 20, that's different from if I do it the other way around. Right? I do 60 divided by 12 and then divide by 4. It's the same for subtraction. 60 minus the quantity 12 minus 4 is 52. That's different from the quantity 60 minus 12 minus 4, which is 44. Okay, so we've got a problem here, right? And you know, what we would like to do, so the associativity rule that we're going to, the convention that we're going to follow, followed by most programming languages, is if an expression has two or more operators in it that have the same precedence level, like divide, then we execute them from left to right order. So for example, here the product parser is trying to parse 60 divided by 12 divided by 4. Which one do we do first? Well, left to right associativity says do this one first. So here's what the output is going to look like. We're going to do 60 divided by 12, and then we're going to divide that by 4. Same thing with sum. So here we have 60 minus 12 minus 4. Our interpretation is we do this one first. We'll do this one first and then this one, left to right. Okay. How do you do this? It's really tricky, and I'm just going to give you like a flavor of it, the way that I do this. So here is my product parser. It's been given this string. And what I'm going to do is just punt on the whole issue of associativity. And the way that I do this is I'm going to turn division into multiplication. So I'm going to turn this string, I'm going to transform it into this string. 60 times 1 over 12 times 1 over 4. That's and then I have a secondary parser that's going to parse that. I'm going to do the same thing with sum. I'm going to turn this subtraction into addition. So 60 plus negative 12 plus negative 4. So 60 plus 12, negative 12 minus 4, right? It doesn't matter then which order we do this in. Okay, so I've done this for you for sum, I think. So here is my sum parser. A sum is one or more products separated by plus or minus. Okay, so here's the sum parser. I begin by starting to parse with product, followed by, here's rep, because it's 0 or more. And then inside here, I'm going to expect to see plus or minus, followed by another product. Okay, now here's the tricky part. We're still inside of rep here. I haven't closed this parentheses yet. I'm going to take just this part of the output of this part of the parser, and I'm going to transform that. If this part of the parser is plus followed by S, S would be this product. I don't know why I called it S. It should be maybe E instead, but whatever. S is the output of this. Then I'm just going to return S. So in other words, I'm dropped the plus sign for you. If on the other hand, it's a minus sign followed by S, then I'm going to negate S. And up here I have a little function that takes, that basically creates the fun call 0 minus whatever. So if it was the, if S, for example, here is 50, right, then this is going to get transformed. This will be expression negative 50. Okay, and I drop the minus sign. And that is the end of the rep. So inside of the rep, I'm doing some analysis. And now I'm going to transform that. It's either P followed by nil, I just give you P back, or it's P followed by the rest. And so now I'm going to do a fun call. The identifier is add, so we're adding, okay, that's the operation. And then P const on to rest. So this is the output of rest, which are all of these positive and negative numbers. And then I'll put in front of the list the output of this first product here. I know it's complicated. You know, we can maybe talk more about it, like office hours, or set up a special session. But this code works, and I've given it to you. Okay, this sum code, this code here, where does it start? Here, so all of this code actually works. So that's a gift from me to you. Thank you, Professor Pierce. Oh, you're welcome. And now here's product. Oh, did I give you product too? Oh my gosh. Oh no, is this a mistake? No, yeah, it looks like it is a mistake. Oh, yeah, okay. Yeah, so here, this is, I think this code is complete as well. And this code is demonstrating an alternative way to enforce associativity rules. Right, so, yikes. I really gave away like the whole store here. So it looks like you've got some end product completely defined here. Wow. All right. Term is correct. Bool is literal is not quite correct because I have not given you these three, but I gave you the other two. So the only thing that's left here is fun call. Here's my grammar for a fun call. It's an identifier followed by operands. And operands, the operands is the only thing that's weird. The output of operands parser is a list of expressions. So operands is a left parentheses followed by, and then what this guy says is one or more expressions separated by commas, but that whole thing is optional. So maybe no expressions followed by right paren. Here are some examples of fun calls. a fun call can have no inputs, exactly one input, or a sequence of inputs separated by commas. So you'll have to implement these two parsers. That is what I'd like you to try to see if you can't get done. And then Tuesday, maybe we can answer some questions, or you can write to me over the weekend if you get stuck. Remember, we have to get this right, because Jedi 2, Jedi 3, they're all going to depend on this code. So we want to be able to get this right. Let's see. Okay, any questions? Yeah, I know, it must be kind of, I know it's boring to sit in a class and listen to somebody talk about code. It must be doubly boring to sit at home. Let's see, you want to see declaration again? Let's see if I can find that. Oh, and let's see. Oops, I just closed the chat window. New class for equality and inequality. No, okay, so that's a good question. So Stan's asking, do we need to create a new class for equality and inequality? That's a good question. The answer is no, because, let's see, where have I lost my code? Here it is. Okay, so here, you're going to do for equality and inequality, you're going to generate, for example, let's say something like this. Let's say the user types in 3 is less than 4. Well, this parses, quotes, so this is a fun call, and I believe the function is named less. So the user types this in at the prompt. Your inequality parser is going to generate a fun call with the operator less and the operands 3 and 4. When we execute this, this goes to the ALU, and this eventually calls so when executed, calls that, right? So equality, inequality, sum, product, they all turn into fun calls, and you already have a fun call class. Let's see, Mignon wanted to see declaration, my declaration class. Let's look at the definition of the declaration class. Let's see where this is. This is the declaration class, which is actually something you're supposed to do. Remember, this is what a declaration looks like. So X here is the name. Add 2, 3 is the expression. Here it extends special form. And then when you execute an expression, okay, you execute the expression part over here. You execute that. That produces, what happens when you execute an expression? It produces a value, right? And then you're going to put that value into the environment and associate it with the name. Remember, the environment's essentially like a hash table. And then you return the notification OK. And to parse it, you look for def, followed by identifier, followed by equals, followed by something that followed by an expression. And if you get all of those pieces, you call the declaration constructor with this is the output of the identifier, and this exp is the output of the expression part. Is that good, Ming-Yang? Good. Anything else? Okay. Well, then have a good weekend. Try to like stay home this weekend. Here in Santa Cruz, they've closed all of the beaches for the weekend. So, because I guess they don't want like people celebrating Easter. I guess it's Easter weekend too. So have a happy Easter if Easter is your thing. And I will see you all Tuesday unless you come to office hours tomorrow. All right. Bye-bye.